In the second part of this chapter, we will talk about the substitution reactions of alkyl halides. Let's first start by a brief introduction of alkyl halides. These are one type of functional groups, and the halides can be, normally we represent them as an X, and the halides can be either an iodine, a bromine, and a chlorine. For this chapter, fluorine is not used as a halide. The reason why, because fluorine is a very bad leaving group because it is the strongest base among all. Halides are classified into primary, secondary, and tertiary alkyl halides, and that classification is very important when it comes to reactions, because reaction conditions are limited by the type of alkyl halide that you are working with, whether it's primary, secondary, or tertiary. Now, all the reactions that we're going to talk about in this chapter, these are specifically for halides that are connected to an sp3 hybridized carbons. Now, for halides that are connected to an sp2 hybridized carbons, like here in this example of the vinyl halide and the aryl halide, these are sp2 hybrid carbons. Since I'm working with a substitution reaction, as we mentioned before, substitution means that I am breaking this bond and I'm replacing this group by another group. But because this group is connected to an sp2 hybrid carbon, which is basically electronegative, so it's pulling more electrons towards it, it's going to make that sigma bond strong. So that sigma bond will not break by the conditions that we are talking about in this chapter. So any halides that are connected to an sp2 hybrid carbons, whether they are vinyl or aryl, and please know what a vinyl and an aryl halide looks like, these are now going to be accounted for in the rules that we are going to mention. So all the rules that we are mentioning are simply for halides that are connected to an sp3 hybridized carbons rather than sp2 hybridized carbons, so that they become a good leaving group. Allylic halides, benzylic halides, these halides, they do participate in the reactions that we are talking about. And last time we defined what an allylic means. An allylic means that you have an alkene. Next to the alkene, there is a carbon. So that carbon, we call it an allylic carbon. So if there are hydrogens on that allylic carbon, then these are called allylic hydrogens. If there's a halogen in there, then this is called an allylic halide or an allylic halogen. So if it's a chlorine, then it's going to be an allylic chloride. So you know that the chlorine is on carbon number 3 of the double bond. This is 1, 2, and 3. Same thing for the benzylic. This is the benzylic carbon. So that is the benzylic carbon. What is a benzylic carbon? A benzylic carbon is a carbon next to the benzene. There is a cyclohexane. I don't want you to confuse between them. There's a cyclohexane and the carbon in there, and there's a benzene and the carbon. This is not a benzylic carbon. So this carbon here is not a benzylic carbon. It's just a regular carbon that is connected to the cycle, to a cyclohexane. This is a benzylic carbon. So when I name this compound, I name it as a benzylic chloride, bromide, whatever. This here, if I want to name it, I would name it as a cyclohexane, methyl, bromide, chloride, whatever. Okay? Or since we are working with a longer chain, then I can name this as, for example, if I have something like this, if I have a chlorine here, then I would name this as a chloromethyl cyclohexane. So that is a chloromethyl, and it's a cyclohexane. It's a parent name because it has more carbons than the one carbon over here. So this is why the basically the name cyclohexane is going to be at the end. So this is going to be cyclohexane, and that is going to be chloro, it's a methyl that is coming off the cyclohexane. I don't have to say that it is one chloromethyl because already methyl is just carbon one, so it's fine. And everything in there is on the cycle, so and the cycle has no substituents, so everything is going to be on carbon number one of the cycle. So I don't even have to mention where the methyl is on the cycle though. So let's continue over here to name just a brief revision of naming alkyl halides. They're going to follow the same rules of naming alkanes. Here now my substituent is going to be the halogen, so I'm just going to name it as a halo form. Bromo, chloro, bromo, and then I need to arrange them in alphabetical order. There are common names for alkyl halides, and the common names we can use in the common names either tertiary, isobutyl, isopropyl. So, and these are used for simple alkyl halides. We can assign a common name for those. See, this is over here. This is an ethyl, and it's a chloride. So it's going to be an ethyl chloride in this case. This is going to be the common name. That is a simple alkyl halide. I can name it as a common name by simply ending the halogen with IDE. If I am to name it as an IUPAC name, then that is going to be basically it's going to be a chloro. I don't have to put one because again the chlorine can either be on this carbon or this carbon and still be carbon number one. So chloroethane, that is going to be the IUPAC name. The common name, you just put an IDE at the end. And that is used for simpler alkyl halides. Now alkyl halides, they do have a polar CX bond. And it's so important to know what are your charges, where is the electron deficient site, where is the electron rich site, because the alkyl halides is going to react with other reagents. So according to these other reagents and their charge, whether there are nucleophiles or electrophiles, I can carry out my reaction. So let's say, for example, if the alkyl halide reacts with a nucleophile, then I know that the nucleophile is going to come and attack the carbon. If the alkyl halide reacts with an electrophile, then I know that the electrophile is going to react with the chlorine. With respect to the properties, physical properties of alkyl halides, they are completely insoluble in water. No matter how many carbons there are in the chain of the alkyl halide. So 1 carbon, 2 carbons, 3 carbons, these are completely insoluble in water, but they are soluble in organic solvents though. So any organic solvent like acetone, like a chloroform, CHCl3, this is a chloroform in there, like dichloromethane, this is CH2Cl2, like carbon tetrachloride. All of those are considered to be organic solvents and they dissolve alkyl halides. With respect to the melting and the boiling point, alkyl halides, they do have higher boiling point and melting point than alkanes that have the same carbon number. The more carbons you have in the chain, the higher is the boiling point and the melting point. The reason why, because the surface area is going to be larger. This is why. And then melting point and boiling point normally increases as the size of the halogen, so as the size of the halogen becomes bigger and bigger and bigger, the melting point and the boiling point is going to increase. Remember that branching normally increases the melting point and it decreases the boiling point. So remember that. Now, with respect to the reaction types of the alkyl halides, there are 2 of them. We're going to consider just the substitution in this chapter. Elimination, we will talk about it in the coming chapter, in the chapter after this one, which is chapter 8. Normally, substitution and elimination, they occur concurrently at the same time. But I'm going to break it down for you. We're going to explain substitution first. and then the next chapter will explain elimination, and then at the end of the next chapter I'll combine both substitution and elimination rules together. But just remember that nucleophiles, they act as bases. So if I have a nucleophile, it's also a base. So my product will be a substitution and elimination at the same time. But let's go ahead and focus on that part first of this chapter. So this is a substitution reaction where the halogen is basically substituted by a nucleophile. So you're going to end up having a leaving a group in this case. Okay. There are a lot of conditions for this reaction, and the conditions for this reaction basically rely on the type of the alkyl halide, whether it's primary, secondary, or tertiary, on the type of a nucleophile, because nucleophiles can be strong, they can be weak, and the type of the solvent. Let me add a solvent in here. Solvents are very important because the solvents are the ones that drive the reactions to completion, and the type of the solvent that I am using in order to get to my product. So all of these are basically important in order to determine what type of mechanism I have in substitution. Normally in substitution there are two mechanisms. There is an SN1 mechanism. This is a nucleophilic substitution reaction, reaction order 1. And then SN2 mechanism, which is a nucleophilic substitution reaction, reaction order 2. So whether I have SN1 or SN2 mechanism, that solely depends on the type of the alkyl halide, the nucleophile, and the solvent. These are the ones that are going to determine the type of the mechanism that I will be working with. But just here, just a general idea, refreshing your memory about substitution. With substitution, you are using basically a nucleophile. The nucleophile normally that you are using has a negative charge, or it can be neutral, either one of those. But if it has a negative charge, please, I keep saying this because I know that you will be confused. Where did the counter ion go? There is nothing called a negative charge in the product without having a positive counter ion balancing it. We omit it from organic reactions for a reason, so we don't show it. We just show the balanced ionic equation without the positive counter ion. So any common ions, we just take them out. This is the way we express organic reactions, but they are there. Every time you have a positive counter ion, you have a negative one to balance it. Okay, so if I want to show you the reagents for this one, I would write NaSH. It's your job to know that this is an ionic bond, so the SH is negative, the sulfur is negative, and the sodium is positive. Here, I would write down NaOCH3. This is my reagent. Here, my reagent is NaOH. Okay, this is a substitution reaction, so I'm replacing the chlorine with the OH, the iodine with the SH, and the bromine with the OCH3. Of course, I'm going to end up having a leaving group because every time I make a bond, I need to break a bond. And the breaking is going to be by heterolytic cleavage. The breaking is going to be by heterolytic cleavage. So the cleavage here is a heterolytic cleavage, where the 2 electrons of the sigma bond add to the bromine to make the bromine having 8 electrons. Okay. Now, with respect to the nucleophiles, as you saw over here, these are my nucleophiles. Now, nucleophiles do have conditions in there. And the nucleophiles, there are types of nucleophiles. As we said, there are types of alkyl halides, there are types of nucleophiles, there are types of solvents in there. The type of each one of them will determine what mechanism I'm going to go by. So let's go with the general explanation of nucleophiles. Nucleophiles can either be negative charges or they can be neutral. If they are negative charges, they are very, very strong nucleophiles. If they are neutral, they are weak nucleophiles. And as I said, always nucleophiles have positive counter ions if they are negative charges. If they are neutral, they don't need any counter ion. Like for example, water. Water is a neutral nucleophile. Why it's a nucleophile? Because it has lone pairs on the oxygen. By definition, a nucleophile needs to have lone pairs. If it has lone pairs and the negative charge, it will be strong. If it has just lone pairs, then it is a neutral. And a neutral means weak nucleophiles. Another example of a weak nucleophile is ammonia, NH3. NH3 does have lone pairs on the electronegative atom. This makes it a nucleophile. But since it is neutral, then that is going to be a weak nucleophile. Always the nucleophiles, they do attack the partial positive, the electrophile. Nucleophiles react electrophiles. So in the reactants, you have to search, where is my electrophile? So your electrophile is the carbon, so the nucleophile attacks it. It is not the bromine. The nucleophiles will repel the bromine because they have same charges, negative, negative. Opposites, they basically attract each other. So this is why the nucleophile is going to attack the partial positive carbon. Now, with respect to neutral nucleophiles, when you are using neutral nucleophiles, there is an additional step that you need to do in the mechanism. And we will talk about it once we discuss the SN1 reactions. The additional step, basically, normally neutral nucleophiles, we use them without solvents because they can act as their own solvents. Sometimes we add solvents to them, but most of the time we use them without any other solvent in there because they can act as nucleophiles and solvents at the same time. So neutral nucleophiles act as a double job. They act as a nucleophile and they act as a solvent. So when I use them, I just use them in excess. So when I use them in excess, the first step is the nucleophile is going to attack the carbon. Halogen is going to leave by a heterolytic cleavage. I'm going to end up getting my substitution product. But remember this and take it as a rule from now on. Whenever you want to form a product, products are always neutral. So if your product is a positive charge, you have to deprotonate. This step, we call it a deprotonation. And normally deprotonation happens by an acid-base reaction. So you have to deprotonate by any base in the solution. Here I'm having an acidic hydrogen. This hydrogen is acidic. Why? Because this hydrogen is connected to the nitrogen. Nitrogen is more electronegative. So the direction of polarization is pulled towards the nitrogen, making this hydrogen partial positive. Any one of these hydrogens are partial positive. So now my nucleophile, which acts as a base now, bases take acidic hydrogen. So this hydrogen is slightly acidic. The base is going to come take this acidic hydrogen in here and form a lone pair. So this is the additional step 2, which is a proton transfer that is always a must whenever you do a neutral nucleophiles, because you're going to end up having a positive product. So you're going to make it a neutral, so you would need to use another mole of a nucleophile that acts now as a base to deprotonate to reach or to make your neutral product. This is an example over here. Your ammonia is going to react to form the substitution of product, and then another ammonia by an acid-base reaction is necessary. It is necessary. It is necessary in here because you cannot leave this as a product. It is not right. Think about it. Your reaction has a base in it. And this is acidic. So it makes sense that the base is going to deprotonate the acid to make the neutral compound. And whenever you make your neutral product, you've reached a stable product in that case. Now, we've talked about the nucleophiles. So to sum up, nucleophiles are two types. There is a strong nucleophile and there is a weak nucleophile. Strong nucleophiles have a negative charge. Weak nucleophiles, they normally are neutral. Whenever I use a weak nucleophile, I have to use it in excess so that I would react it twice. The last time I reacted, normally you do a deprotonation. You deprotonate your product in order to form your neutral product form. Now for the leaving group, there are conditions for this leaving. This is my leaving group. So whenever I talk about the leaving, we've done from the nucleophile conditions. Now, the leaving group. The leaving group, in order to leave, in order for this sigma bond to break by a heterolytic cleavage, that leaving group has conditions. It has to be a weak base. It has to be a weak base. So it needs to be its acid needs to be very, very strong so that it is a weak base. So if I am looking in here, if the halogen is a chlorine, I know that HCl basically is, if I look at the acidity, I know that HCl is basically less acidic than HBr, than HI, because of the size of the ion, right? Okay, this is HF. HF is going to be the least acidic among them, and HI is the most acidic because the conjugate base is a larger anion in this case. Now, since HI is the strongest acid, its conjugate base, which is the I minus, is very weak. So that makes iodine, I minus, that makes it a very good leaving group among all of those. So I minus, Br minus, Cl minus, they are good leaving groups, but F minus, because that guy over here is the conjugate base of the weak acid, so it is a strong base, it is not going to be a good leaving group. Remember the trend of basicity in a period. Basicity is the opposite of acidity. So we're going to go with opposite of electronegativity in order to look for basicity. So the more electronegative, basically the less is the base. It's opposite to acidity. So in this case, nitrogen is less electronegative than oxygen. Then nitrogen is going to be more basic than oxygen. So I know in this case that water is going to be less basic than NH3. So water is going to be a better leaving group than NH3 in this case. Remember, leaving groups have to be weak bases. In this chapter, we are limited to X being any of these halogens. In the coming chapter, X is going to be water. So X is going to be water. X can be NH3. So X can be another leaving group other than these halogens. But in this chapter, I'm just limited to these halogens in there. So please know that I minus leaves faster than Br minus than Cl minus because these are conjugate bases of, they are weak conjugate bases of strong acids. There are other leaving groups in there. So all of those are considered to be an excellent leaving groups. And because these are conjugate bases of strong acids, so they are weak bases. Now I have here, I have these to be a bad leaving group. So all of those are bad leaving groups. In the coming chapters, we will talk about OH, and OH is a very, very bad leaving group. Very bad leaving group. Why? Because it's a strong base of a basically of a weak acid. So this is why it's a bad leaving group. So any of those, these are very poor leaving groups. So the substitution reaction cannot happen with any of them. The leaving groups have always to be weak leaving groups for substitution to happen. Now with respect to the nucleophile and bases, just to differentiate and to explain the term nucleophile and a base, both have lone pairs, but the way that they use their lone pairs is different. Bases use their lone pairs in order to take a hydrogen, in order to form a bond with the hydrogen. Okay, this is how the bond is formed. So bases uses the lone pairs to form a bond with the hydrogen. And we call it bases attack protons. This is the difference between bases and nucleophiles. And nucleophiles, on the other hand, uses its lone pairs in order to attack an electron deficient site. So that carbon needs to be partial positive so that the nucleophile attacks it. See the difference? Both have lone pairs, and bases are nucleophiles. So we have all the examples of bases, most of them. They are nucleophiles. So how would you know which is which? Well, basically they're going to act as both. So you're going to get both products in there, elimination and substitution. If you are using a base, then your product is elimination. That is for chapter 8. For this chapter, we're using a nucleophile. The nucleophile uses its lone pairs in order to add to the electron deficient site in there. So you're going to end up having a substitution product. Every time you form a bond, you break a bond. So you're going to end up having leaving a group in there. The weaker the base, the better is the leaving group, the easier that it's going to leave. Remember that. So to define basicity and nucleophilicity, basicity is a measure of how readily an atom donates an electron pair to a hydrogen. Bases take hydrogens. Nucleophiles, no, they use their lone pairs in order to attack the electron deficient atom. Rules for basicity. Nucleophiles and bases can be the same or they can be different. And that actually depends on the solvent that is used. Now, normally there are conditions where always nucleophiles are the same as bases. And these are the 3 conditions in there. There are other conditions where nucleophiles and bases are different. And these, they do depend on the type of solvent that I'm using. So for the cases where nucleophiles are the same as bases, if you have 2 nucleophiles, like OH and an acetate, this is called an acetate base. This is the conjugate base of acetic acid, and you're gonna have this type of acid in your homework in the top hat assignment. So this is the acetic acid over here. This is my acid. This is where the nucleophilic site is. This is the oxygen. It's not this carbonyl. No, it is this oxygen here. So that is going to be your neutral nucleophile over there. This is called acetic acid. Its conjugate base is called the acetate ion. Okay, anytime you have a negative charge, you have a positive counter ion to balance it. Sodium, potassium, whatever. Same thing in here. So if the nucleophiles, they share the same electronegative element. See, they share the same electronegative element. Normally, we compare their pKa values and we go by the rule that the stronger the base, the stronger is the nucleophile. Here, OH is a stronger base because the acetate in this case comes from an acetic acid. So if this is a carboxylic acid, it is acidic. So its conjugate base is weak. It's an acid by itself. This is different. OH comes from water. OH comes from water. Acetate comes from acetic acid. This is an acid. You don't have to look at the pKa. It is a carboxylic acid. This is an acidic hydrogen over here. So if this is an acid, then its conjugate base is going to be weaker. It's going to be weak. Then if the conjugate base is going to be weak, then we are going to go by the rule, the stronger the base, the stronger the nucleophile. This is more basic, then OH is a stronger nucleophile than the acetate. Another rule is negative charge nucleophiles, they are always stronger. They are always stronger nucleophiles, stronger bases than their conjugate acids. So if you have a nucleophile that is negative, and if you have a nucleophile that is neutral, see, both of them, they share oxygens in there. So you need to share the electronegative element in there. So both of them are sharing oxygens. So you go with the charge. The nucleophile that has a negative charge is the strongest. and the nucleophile that it has a neutral charge or is a neutral, that is going to be the weakest. And then we're going to go with the third rule now across the period of the periodic table. And we're going to say that from right to left across the period of the periodic table, nucleophilicity normally increases. So as the basicity increases, the nucleophilicity increases. This is when also nucleophiles and bases are the same. Now, there are some times that nucleophiles and bases, they are not the same at all. Not the same. Because you do have bulky bases, and these bulky bases can never ever act as a nucleophile because they're steric hindrance. Like, for example, sodium or potassium. So this is potassium over here, or sodium. Tertiary butoxide. So sodium or potassium tertiary butoxide, normally I abbreviate it like this. I do K. This is K plus, and then an O, and you write simply your the condensed formula in there. This is a CH3. This is a 3 over there, and this is a negative charge. So this is how normally we write it down in the reaction. This is potassium tertiary butoxide. Potassium tertiary butoxide is a bulky base. Why it is a bulky base? Because see all of these CH3s, they are basically hindering those lone pairs in there. They are in the way of these lone pairs being used to make a substitution product. So this is why potassium tertiary butoxide, it just acts as a base. It only takes a small hydrogen atom. It cannot act as a nucleophile. No way it will. Compared to an ethoxide, this here is a smaller R group next to the oxygen, so it allows the nucleophile to use its lone pairs to bond with another carbon. So if you have a carbon and a halogen in there, then this nucleophile can simply add, halogen can leave. But with this one, if you have a carbon and a halogen, it won't, because all of these lone pairs, they are hindered by the bulky CH3 groups. So there is no way that these lone pairs are going to be used to attack this carbon and allow the halogen to leave. So no substitution with these. And with these types of bases, these only act as bases. They can never ever act as a nucleophile. So remember, nucleophiles, they attack the partial positive carbon. Bases, they attack hydrogens. This is the difference between both. When I'm using a bulky base, we call those non-nucleophilic bases. This means that there is no way that they can attack a partial positive carbon. They only act as bases, and bases take acidic hydrogens. Now with respect to the solvent effect on the nucleophile, on the nucleophilicity. How nucleophilic is your nucleophile is affected by the type of solvent that you use. Because that solvent is going to drive your reaction. It's going to either make it a fast or a slow reaction. There are two types of solvents. We're going to limit ourselves in this chapter with polar solvents. Of course, there are non-polar solvents, but honestly, we're not going to go there. We're just going to stick to polar solvents in there. So there are two types of solvents: polar protic and polar aprotic. And these types of solvents will also drive the type of mechanism of the reaction, whether SN1 or SN2. For polar protic solvents, these solvents, they contain OH bonds and NH bonds in there. So let's have, for example, if you have a nucleophile, any nucleophile, here I am using sodium bromide. So if I have, for example, so the reaction is going to be like this. I have an iodine in here. This is my alkyl halide, and I am reacting this with sodium bromide. Okay, this is positive, this is negative. And the solvent that I am using is polar protic solvent. Polar protic solvents are solvents having OHs and NHs. Like, for example, here, these are different polar protic solvents. All of these solvents, they do have OHs in them. Okay, I can use ammonia. Ammonia can also be a solvent in there, and it has an NH, and it's considered a polar protic solvent. So if I use a polar product solvent, like in this example, I'm using water, what it's gonna do? Water is going to basically arrange itself around the cations and the anions of my nucleophile. And when it does, water is going to try to solvate the cations by an ion dipole interaction, and it's going to solvate the anions by simply, since I'm using here bromine, by hydrogen bonding. If I'm not using a bromine in there, then I will have the ion dipole interaction. But in other words, the polar product solvents, they dissolve both cations and anions. So here in this case, if I am using a strong nucleophile, then the nucleophile is going to be dissolved in the solvent. So that is going to affect the strength of the nucleophile in the reaction. So if I am working with smaller, more electronegative nucleophiles and ions in there, these are going to dissolve in these types of solvents. So in polar product solvents, normally nucleophilicity increases down the column of the periodic table as the size of the anion increases. That is going to be opposite of basicity. I made a small chart in there for polar product solvents. So in a period, normally nucleophiles and bases are the same. In a group, no. Nucleophiles are opposite of bases. I know that bases, they increase as the size of the ion becomes smaller. So the basicity trend is from bottom to top. As I go up the periodic table in a column, the basicity is going to increase. So basically F is going to be more basic. F minus is going to be more basic than Cl minus, then Br minus. This makes the nucleophilicity being the opposite. The nucleophilicity is going to be the opposite of basicity. So the nucleophilicity is going to increase down the group as the size of the anion being larger. So that is a small table in here that you can use to solve problems. Now with respect to polar aprotic solvent, these solvents, they are easy. They don't have any OHs or an H bonds in there. See all of these solvents? You are required to know. As I told you at the beginning, there are parts in organic that you have to know and you have to memorize. One of them is functional group, the other one is the rules of naming, the third one is the reagents or the solvents and their structures in there. Acetone is a ketone, and that acetone is a common organic solvent. Dimethyl sulfoxide, we don't use that solvent too much because it is kind of like nasty to get rid of. With acetone, I can evaporate, I can get rid of. But DMSO and DMF, these are kind of like nasty and they have a very bad smell. But sometimes with certain reactants, these are the only solvents to use to dissolve them. So this is why I have to use those. As you can see, these solvents, they don't have any OH or NH bonds, so this is why I call them aprotic solvents. Same thing for acetonitrile. Also, this one has a very bad smell. Tetrahydrofuran is okay, and we use also that, we abbreviate it as THF. All of those are considered to be polar aprotic organic solvents. Now with polar aprotic solvents, this is the difference between polar aprotic and polar protic. Polar protic, they dissolve both cations and anions. But polar aprotic, no. They dissolve only cations by ion dipole, but the anions in there, they don't. They don't dissolve them at all. So we call them naked basically. The anions stay in the solution in there. So if I'm using a strong nucleophile, the solvent will not mess up with that strong nucleophile. So that strong nucleophile will stay strong. And this is very important. That strong nucleophile will stay strong. So if you wish your nucleophile to stay strong and you want to proceed with the mechanism, you have to use that type of solvent. If you want your nucleophile to be solvated, then you have to use the polar protic solvent. This is another small table over here. So now for aprotic solvents, with respect to aprotic solvents in there, nucleophilicity is the same again as basicity in a period. Now in a group, it's also the same. So as basically basicity increase, as a nucleophilicity is going to increase. So these two tables in there, you can have them with you if you want in the exam. Just write them down on a piece of paper and use them to solve problems in the exam. There are, in your homework, there are some problems where I'm asking you to arrange nucleophiles in an increasing order basis, in an increasing or decreasing order versus one solvent over the other. So you can use these tables in there. There are examples of oxygen in nucleophiles, nitrogen in nucleophiles. So nucleophiles can be divided into negative nucleophiles. Negative nucleophiles are strong nucleophiles, and as I said, all of these, they should have positive counter ions that balances them, any positive metal. And then we have a neutral nucleophiles. The neutral nucleophiles can be water, alcohols, derivative of nitrogens. I can have hydrogen sulfide, and I can have the alkyl, basically alkyl thiols in this case. This is an RSH. SH is a functional group for a thiol. So in this example over here, we can use these two tables in order to basically answer the question. So the question is, rank the following in order of increasing leaving a group. So I do have my water, my hydrogen sulfide, and my ammonia. Just remember that the weaker the base, the better is the leaving a group. Okay. Now I know that sulfur is the least basic, sulfur oxygen. So comparing sulfur and oxygen, sulfur is the least basic in that case. So since sulfur is going to be the least basic, sulfur is going to be the best leaving a group. And then comparing oxygen to nitrogen, nitrogen is going to be the most basic, so it's going to be the worst leaving group in there. Rank these species in order of increasing nucleophilicity, and this is how the question can be. I can give you a series of nucleophiles in a solvent and ask you just rank them in terms of increasing nucleophilicity based on their interaction with the solvent in here. So you have to check that solvent. What type of solvent is it? This one is a polar product solvent. So I know that with polar product solvents here, so let me magnify this guy over here, take it here, just go ahead and magnify that. Okay, so with polar product solvents in there, I know that the nucleophilicity is opposite of basicity when I'm working with a group, and it's the same as basicity when I'm working with a period in there. Sulfur and oxygen, these two, they are in a group. So I know that as basicity increase, as a nucleophilicity decrease. So this is going to make that guy over here more nucleophilic than the ethyl oxide. Now for two compounds that, let's say over here, we have these two compounds that have the same, they share the same oxygen atom. So we know that the more basic is the more nucleophilic. So since this one is the conjugate base of a strong acid, this one is a weak acid in this case. So it's going to be basically less nucleophilic than the ethoxide. And this is going to be my order. Now let's do another one with acetone. Okay, with acetone now that is going to be a polar A product solvent. So with polar A product solvent now we're going to use that small table over here, polar A product solvent, and these are the trends of basicity that parallels the nucleophilicity when I am working with a group, and then if I'm working with a period it's still the same. So basically with polar A product, nucleophilicity is the same as acidity, same as basicity, I'm sorry, in both periods and the groups in there. So by using this trend I can easily solve this problem over here.